Every distributed system, every system running on more than one machine, must make a fundamental trade-off. When a network failure occurs and your machines can't talk to each other, what does your system do? Does it keep accepting requests and risk returning inconsistent data? Or does it refuse to respond until the network recovers? This is what the CAP theorem captures. It's one of the most important theoretical frameworks in distributed systems, and it comes up constantly in senior-level system design interviews, not as a trivia question, but as a lens for evaluating architectural decisions. Today, we'll break down the CAP theorem, explain what it actually means in practice, and walk through the consistency patterns you'll use to make these trade-offs concrete. The CAP theorem was proven by Eric Brewer and Nancy Lynch in 2002. It states that a distributed system can only guarantee two of three properties: consistency, availability, and partition tolerance. Before we discuss the trade-off, let's define each property precisely. Here's the key insight that makes CAP practical. In any real distributed system, network partitions are not theoretical. They happen. Cables get cut. Data centers lose connectivity. Network switches fail. Because partition tolerance is mandatory for any real distributed system, the actual choice is always between consistency and availability during a partition. That's why you'll hear people say CP versus AP rather than pick two from CAP. CP systems, consistency, plus partition, tolerance, choose to reject requests rather than return stale data when a partition occurs. HBase, ZooKeeper, and traditional relational databases fall into this category. Banks use CP systems. You'd rather get an error on a wire transfer than have it succeed with wrong data. AP systems, availability, plus partition tolerance, choose to keep serving requests even if some data might be stale, and resolve conflicts once the partition heals. Cassandra, CouchDB, and DynamoDB are AP by default. Social media feeds use AP systems. Seeing a tweet from 2 seconds ago instead of 1 second ago is acceptable. Let's be precise about what network partition means at scale. In a 1,000-node data center, network partitions, where some nodes lose connectivity to others, happen every single day. Hardware fails, switches reboot, BGP routes flap. The probability of zero failures in a 1,000-node cluster over a 24-hour period is effectively zero. At Google's scale, individual machines fail at a rate that makes failures a constant background condition, not an exceptional event. This is why the CAP theorem's implication, partition tolerance is not optional, is not a theoretical concern. It is an operational reality. Every system design that involves more than one machine must have an answer to the question: what does this system do when two of its nodes can no longer communicate? The uncomfortable truth is that CA, a system that sacrifices partition tolerance, is not a real option in a distributed system. It describes a single-node system, which by definition can't be partitioned. The moment you add a second machine, you've accepted partition tolerance as a requirement. The choice collapses to CP or AP. ZooKeeper is a canonical CP system. It's used for distributed coordination, leader election, configuration management, service discovery. In ZooKeeper, every read returns consistent data. If a ZooKeeper node is isolated from the cluster, it stops responding rather than serving potentially stale state. Kafka uses ZooKeeper for leader election. Hadoop uses it for name node failover. In these use cases, serving stale data would be catastrophic. A split-brain cluster could corrupt data. Cassandra is a canonical AP system. A Cassandra node that is partitioned from its peers will continue accepting reads and writes. When the partition heals, The nodes reconcile using last write wins semantics based on timestamps. This is the right trade-off for a system handling billions of writes per day from globally distributed clients. Brief inconsistency is acceptable. Downtime is not. DynamoDB is interesting because it is tunable. By default, DynamoDB is AP. Reads can return stale data from any available replica. But you can request a strongly consistent read, which routes your request to the leader replica and waits for confirmation. This converts that read to CP behavior at a cost of higher latency and doubled read capacity unit consumption. DynamoDB lets you make the cap choice per operation. Cap gives you the binary choice, but in practice, consistency is a spectrum. Let's walk through the main consistency models, from strongest to weakest. Eventual consistency is the consistency model of most large-scale internet systems. Your Instagram follower count, your Amazon cart, your DNS records, all eventually consistent. Changes propagate and the system converges, but not instantly. Read your writes is a common middle ground. After you post a tweet, you immediately see it in your feed. That's a read your writes guarantee. Other users might not see it for a few hundred milliseconds while replication catches up, but you always see your own actions immediately. Let's put numbers to eventual. In Cassandra with default settings, consistency level 1, asynchronous replication, typical convergence time between nodes in the same data center is under 100 milliseconds. Across regions, it's bounded by the inter-region network latency, typically 50 meters to 200 meters. In practice, for the vast majority of reads, by the time a user makes a second request, convergence has already happened and the stale window has closed. This is why eventual consistency is often less scary in practice than it sounds in theory. The system is not inconsistent forever. It is inconsistent for tens to hundreds of milliseconds, after which it converges. For a social feed or a product listing, this is invisible to the user. For a bank account balance, it is not acceptable, which is why financial systems use synchronous replication and strong consistency at the cost of higher latency. CAP only describes behavior during partitions, but partitions are rare. What about normal operation? The Parcells model extends CAP. Even when the system is healthy, no partition, you still face a trade-off between latency and consistency. High consistency means coordinating across nodes, which adds latency. Low latency means reading from the nearest replica, which might serve stale data. This is why Cassandra lets you configure consistency level per query. You can ask for quorum, majority of nodes must agree, when consistency matters, or just one node responds, when speed matters. The quorum arithmetic is worth understanding precisely. In a Cassandra cluster with a replication factor of 3 copies of each piece of data, a quorum requires 2 nodes, 2 plus 1 chas 2.5, rounded down to 2. If you write to 2 nodes and read from 2 nodes, there is guaranteed overlap. At least one node that served your read also received your write. Therefore, you always read the latest write. This is the middle path between consistency and availability. Quorum writes and quorum reads give you consistency under normal conditions, while still tolerating the failure of one replica per partition. All, requiring all replicas to respond, gives you stronger guarantees but eliminates fault tolerance. One, requiring only one replica, gives you maximum availability but permits stale reads. Here is the single most impactful thing you can do in a system design interview involving distributed databases. Make the CAP choice explicit. A weak candidate picks a database without discussing CAP. I'd use Cassandra for the user data. A strong candidate connects the database choice to the cap position. I'd use Cassandra for the activity feed because we're choosing AP. We'd rather serve a feed that's a few hundred milliseconds stale than refuse to serve it during a network event. We can accept eventual consistency here. The framework has 3 steps. Step 1. Identify the consistency requirement. Ask if 2 nodes in this system return different values for the same key, what is the consequence? If the consequence is money lost, data corruption, or a safety violation, choose CP. If the consequence is a user seeing a slightly stale counter or a feed that's momentarily behind, AP is fine. Step 2. Articulate the partition scenario. Say it explicitly. During a network partition, this system will, and complete the sentence. Either reject requests until the partition heals, CP, or serve potentially stale data and reconcile once connectivity is restored, AP. Interviewers want to hear that you've thought about the failure mode, not just the happy path. Step 3. Choose the database that matches. CP, PostgreSQL, MySQL, HBase, ZooKeeper, etc. AP, Cassandra, DynamoDB, default, CouchDB, React. Tunable, DynamoDB with strongly consistent reads, Cassandra with quorum or all consistency. One more nuance that impresses senior interviewers. CAP describes a binary choice during a partition, but the real world is rarely binary. Most production systems engineer for graceful degradation. An AP system that serves stale data during a partition might also implement a circuit breaker that detects when data is more than 5 minutes stale. Beyond that threshold, the system falls back to showing a cached value with an explicit data may be delayed message, rather than silently serving old data as if it were current. This is not captured by CAP's taxonomy, but it's what mature production systems actually do. Network partition probability. In a data center with 1,000 nodes, the probability of at least one network event, packet loss, switch failure, NIC issue, causing some nodes to be temporarily unreachable is non-zero every day. Google's internal research, referenced in the Chubby paper, cites network partitions as a regular occurrence in their infrastructure. Plan for partitions. They happen. Cassandra eventual consistency lag. In a typical deployment with replication factor 3 and consistency level 1, the lag between a write and the write appearing on all replicas is under 100 milliseconds within a data center. Cross-region replication adds the inter-region network latency on top, typically 50 ms to 200 ms for major cloud region pairs. For 99.9% of use cases with eventual consistency, convergence happens before the user submits a second request. ZooKeeper leader election time. When a ZooKeeper leader fails, a new leader is elected within 3 to 5 seconds. During this window, ZooKeeper is unavailable. It refuses all reads and writes to maintain consistency. This is the CP trade-off made tangible. 3 to 5 seconds of unavailability in exchange for never serving stale data. For distributed coordination, this is the right trade. DynamoDB strongly consistent read latency, approximately 1 to 5 milliseconds for a strongly consistent read which routes to the leader replica, versus 0.5 to 2 milliseconds for an eventually consistent read. The cost of consistency is real, but measured in single-digit milliseconds. Google Spanner achieves external consistency stronger than linearizability in a distributed sense across globally distributed data centers using TrueTime, which relies on GPS clocks and atomic clocks in each data center. Commit latency, 5 to 10 meters within a region, 50 meters to 150 meters globally. Spanner is the existence proof that strong consistency at global scale is possible. It just requires GPS atomic clocks and Google-scale infrastructure investment. The CAP theorem tells us that during a network partition, which happens in all real distributed systems, you must choose between consistency and availability. CP systems prioritize correctness. They'll return errors rather than stale data. AP systems prioritize uptime. They'll return possibly stale data rather than reject requests. Consistency is a spectrum: strong, sequential, eventual. Read your writes. Most large-scale systems use eventual consistency with read your writes guarantees for UX. In interviews, make the CAP choice explicit. Identify the cost of inconsistency in your system, state your CP or AP position, describe what the system does during a partition, then name the database that implements that choice. This level of precision separates strong candidates from exceptional ones. Partitions happen daily in 1,000-node clusters. Cassandra's typical eventual consistency lag is under 100 meters within a region. DynamoDB's strongly consistent read adds 2 T3me over an eventually consistent read. ZooKeeper accepts 3 to 5 seconds of unavailability to guarantee consistency during leader election. These are the numbers that make CAP concrete. In the next video, we cover consistent hashing, the elegant algorithm that solves the data distribution problem and makes adding or removing nodes from a distributed system almost painless. See you in video 8.